Continuing from stakeholder analysis, we have the containing system. It represents the broader hospital IT infrastructure and electronic health record system that our application must eventually integrate with. Finally, in terms of stakeholder analysis, um, we have the external environment, which includes regulatory bodies, insurance providers, and the academic research community, which all influence standards and adoption. Moving on, let's look at the primary stakeholders. Focusing on our direct stakeholders, we identify four key groups. So we have plastic surgeons, cosmetic surgeons, have a high interest and high influence. Their primary concerns are accuracy, reliability, and seamless workflow integration. Patients have high interest but medium influence, and they are most concerned with the understanding and the condition, understanding their condition, and ensuring data privacy is upholded. Clinical administrators and hospital IT have high influence but varying levels of interest. Administrators are focused on cost effectiveness and compliance, while IT is concerned with data security and system maintenance. Um, this analysis guided our design to balance clinical utility with enterprise level requirements. I'm moving on to the next slide. Functional requirements. Now, based on the analysis, we define a clear set of functional requirements. As you can see, all core capabilities for a functional prototype have been implemented, from image upload and landmark detection to scoring and data export. Here you can see all the requirements that have been, excuse me, that have been implemented so far. Let's move on to slide 8 now. Now, non-functional requirements. Beyond functionality, we also focus on critical non-functional requirements. We targeted a performance benchmark of under 10 seconds for the entire analysis pipeline. For usability, we designed an intuitive 5-step workflow. For reliability, we implemented graceful error handling, and for portability, we built the system on a standard Python stack, ensuring it can be deployed on any machine with basic dependency. I think that is it on this side. Obviously, we also have usability, good interface, clear, blah blah blah. Moving on to slide 9. Our case overview. So, our use case diagram illustrated the distinct roles, right, for our two primary actors. We have a patient, and we have the clinician, the doctor, the plastic surgeon, the whatever. While both can access core features like uploading an image, reviewing landmarks, and analyzing scores, the clinician has exclusive access to advanced features like viewing the regional breakdown, exporting raw data, and adjusting detection settings. This tiered access ensuring the tool is both a powerful diagnostic aid um, for professionals and an accessible educational tool for patients. So it is quite versatile. It is quite versatile. Now let's look at the system architecture. I'm trying to make this a bit bigger so it can be seen better. Okay, I guess that's all right. So the system is built on a classical three-tier architecture. The presentation layer is Streamlit based web interface. The application layer is the AI analysis engine that orchestrates the workflow and manages state. And finally, the data layer. This contains the core of our IP, the media pipe model, our custom asymmetry calculation, algorithms, and results storage. We are proud to have built this entire prototype on a powerful foundation, open source technology. Um, Python is the core language I used, with MediaPipe providing AI framework. Streamlit allowed for rapid user interface development, while Plotly and OpenCV power our interactive visualizations. And of course, the entire mathematical engine is built on the high performance shoulders of NumPy and SciPy. Um, Moving on, I don't think I touched on pandas, but pandas is also there. Um, Moving on. So, our class diagram, my class diagram, the object-oriented design that I use promotes modularity and maintainability. The Streamlit app class acts as the central controller, orchestrating data flow between the image processor, the face landmarker, the core symmetry logic engine, and um, the final report generator. This separation of concerns makes the system easier to debug, maintain, and extend in the future. Um, Now, moving on. Um, Sequence diagram. This just analyzes the workflows that we used, and I can explain. So this sequence diagram illustrates the oh, illustrates the chronological flow of a typical analysis session. It begins with the user uploading an image, can be anything, which is processed and sent to the face landmarker. The resulting coordinates are then used for both 3D visualization and the core asymmetry analysis. Uh, the final step is the generation of the clinical report. This entire sequence is designed to be fast, efficient, and intuitive. Um, yeah, as you can read. Um, Now moving on to activity diagram. So the activity diagram just kind of provides a flowchart view of the user journey. Um, it highlights the key decision point after an image is uploaded. The system the system checks if a face is detected. If successful, proceeds through visualization and scoring to the final report. This ensures a robust and predictable user experience. So this is the AI and machine learning pipeline. Now let's look inside this inside the black box, the white box. Our AI ML pipeline is a five stage is a five stage process. Is It starts with input image, which is pre-processed. The detection stage uses the media pipe model to extract the 468 landmarks. The processing stage converts these to 3D coordinates and establishes the facial midline, which you'll see in the demo. How it all works. The analysis stage applies our custom scoring logic. Finally, the output stage delivers the 0 to 1,000 score and the clinical reports. That is the pipeline. Moving on to a our scoring and how we calculate our reference axis. So the first step is in our scoring algorithm is to establish a stable sagittal midline. To do this, we use a robust linear regression model fitting a line to a set of 10 stable anchor points on the face, such as the forehead, the nose tip, and the chin. So this line goes down exactly through the middle as you would want it to be. This mathematical approach ensures that our reference axis is independent of minor head tilts or rotations in the input photo. A critical step, 1 million% needed for which ensures accuracy and efficiency. Moving on to slide 7, normalization. The crucial step is normalization. A 5 millimeter deviation on a small child's face is far more significant than the same deviation on a large adult face, right? To account for this, we normalize all measurements against the patient's bizygomatic width, the distance between the cheekbones. Zygomatic bones are the bones that we call for our cheek, zygomat. This makes our scoring scale invariant and clinically relevant across different patients. So we make sure we measure the distance between zygomatic points. Um, this just ensures that it has the same deviation as faces with different measurements. Now, our precision formula. The final step is our precision formula. This converts normalized geometric data into a clinical score. The formula takes the normalized deviation, subtracts a small noise floor to account for natural micro asymmetries, and then multiplies the result by a sensitivity constant to scale it to our 0 to 1,000 range. This allows me to tune the algorithm for clinical significance as well. Now, moving on to severity classification. Now, here is my way of classifying and quantifying a symmetry level. So this is a 0 to 1,000 score is then mapped to a clear Fortis severity classification system. So if someone is completely symmetrical, they'll get a scoring range of 0 to 10. This is almost like this kind of level of symmetry you'll probably only see with really attractive people, supermodels, actors. You get the gist. But moving on to how we quantify this and the different categories. So we have symmetrical, mild asymmetry, moderate asymmetry, and severe asymmetry. Um, oops, excuse me. Anyone with severe asymmetry will most likely need some form of plastic surgery, obviously if they want. But if it's this severe, then it's probably also causing them health problems, or like closing the air gaps, but it's more something else. This whole system provides clinicians with an immediate and intuitive understanding of the gap between raw data and actionable insight. Um, Moving on to slide 20. So, project timeline. The Gantt chart provides our project execution. We follow the four-phase plan from initial research and requirements analysis through core development, UI integration, and finally testing. I am pleased to report that um, all milestones were met and the project was completed on schedule. Obviously, this is a prototype, and I believe. Oh, we can. Sorry, let me just continue. So, next developmental steps, because this is obviously a still a prototype. I'd like to also add these kind of functions, video analysis. Maybe do it while you're moving in real time and giving an analysis right there in real time. Longitudinal tracking, patient's database integration to visualize progress and asymmetry changes over multiple sessions. This way, um, patients can directly see over a span of time if the changes that they are trying to make are actually working for their symmetry. Clinical validation, IRB approved comparative study against traditional uh, caliper measurements to validate accuracy, and cloud development, secure HIPE compliant web nesting to hosting to allow remote patient monitoring and multi-clinical access. Obviously, we want to make sure that everyone's images are all saved and and held. But obviously, this is more in the long term, for if used in a clinical way, where um where clinicians can actually keep images of their patients so they can see improvements, or any changes. But for a normal person, you'd want their image to be deleted straight away. But this is just the ideas and next developmental stages. In conclusion, um, we have successfully bridged the gap between subjective observation and objective analysis. We replaced manual estimation with AI-driven precision, established a standardized score, and in terms of feasibility, it has developed this project has delivered a cost-effective, accessible software solution that runs on hardware without specialized sensors. If you have any questions, please let me know. Thank you for watching, and I hope you have enjoyed my presentation. This is Sasigrada W1947920, and thank you for watching.